Welcome to Maths for All. I'm Aisling Flynn. This is Statistics 1.9 Sample Variability. Sampling. Usually it is difficult to collect data from a full population. So if you were interested in studying the citizens of a given city, it would be very difficult to ask each individual citizen your question. So you would choose a sample instead, a selection, a smaller group of the population. In something like manufacturing, let's say microchips, the product needs to be tested, okay, for quality assurance. But in the testing, the microchip can be tested to destruction, so it is destroyed by the process of testing, and you can't do this with every single microchip or you'll have none left to sell. Okay, so in that case, let's say every 500th microchip is tested or something like that. Okay, so a sample is taken from the full population of microchips. A sample or many samples can be taken from the population instead. The aim of sampling is to draw reasonable conclusions. So if the microchips chosen are fine, there's no faults in them, and they're pretty reliable, then we can conclude that all the other ones that weren't tested should be fine also. Okay, and if you can take a sample of people and get some answers from them, well then you can say, well, the rest of the population would be similar from them. Okay, we hope that a sample represents a population as a whole, so we would like that it resembles the full population, and for this to be the case, the sample must be random. Okay, so whatever you choose, you don't know anything about them really in advance, and each piece of data has an equal chance of being included. So this is illustrated in this picture. So the population is all the red dots, whatever they could represent people. Okay, and there's a possibility to choose many different types of samples. You would randomly perhaps throw down a circle and take whatever dots are inside the circle. You could decide in advance how big your sample is going to be. That's an important thing we'll see soon. Okay, so and you can see that the samples can be different from each other. Okay, but then you can draw conclusions from that also. So sampling distributions. Here's an example. Valerie Linton and Ronald Stump are competing in a presidential election in the US. Linton's campaign manager goes to Florida to take a poll to see who is likely to win that state. She travels around Florida and questions groups of people in different districts, so she's taking different samples. In each district, her sample size is 500, so she asks 500 people who are they going to vote for. So sample 1, and I'll explain the notation in a moment. P with a little hat, P hat equals 0.48 for Linton. So 48% of sample 1 say they'll vote for Linton. Sample 2 is 43%. So the proportions are given in decimal. But if you want to translate them to what you would normally talk about, percent, we would multiply by 100, okay? Divide by the 100, go backwards. So 43%, sample 3, 45%, sample 4, 47%, okay, or 0.47. So this is not looking great for her. Now P hat, so P with that little triangular rooftop hat on top, is known as the sample proportion. So it's the proportion that say, yes, I'll vote for Linton. Is P hat from the sample. Okay, so it's not looking great for her. Okay, but these sample proportions, they may differ from the true population proportion, which is just regular P. Okay, so she's getting a feeling from the samples, but yet we can't say for sure because she didn't ask every single person in Florida. Okay, so it is clear from the results that Linton is behind in the Florida vote with slightly less than half the vote. If the campaign manager took enough samples, so took lots more, she would find that the average of the sample values would give the same result as the population proportion, as the real value on voting day. Okay, so that means asking more and more people, you get closer to the actual reality. Okay, and the sample values would be normally distributed about the population value. So what does that mean? It means that if you took enough samples, right, let's take the population value there as regular P. Okay, some sample proportions are below P and some are above P, some are right at P. Okay, but if you took enough samples, well, they would be distributed normally, as we saw the normal distribution, around the population proportion there in the middle. Okay, and it turns out Linton went on to lose Florida with 45% of the vote. Okay, so the samples were representative somewhat. Margin of error. Linton's campaign manager followed on to Georgia. She had only completed one sample survey of 500 people when Linton rang for an update. So she only had one sample of 500 people. And the sample A, we call it, gave back a proportion of 0.52. That 52% of that sample were going to vote for Linton. So she can say that, yes, you're ahead here in Georgia. Or can she say that? So how reliable is this result? It's only 500 people out of a whole state. Is the sample size sufficient? Did she ask enough people? There is likely to be some error. Okay, it's likely to be not exactly 52%. And the true value is likely to be a little different. But how different is the question? We use what's known as the margin of error. So we're going to give some indication as to how different the true population value might be. Okay, so how do we do that? The margin of error depends on the sample size. The larger a sample is, the smaller the error will be. Okay, the more people you ask, the closer it will be to the true population value. A larger sample will have a closer result to the population result. And this is our definition of the margin of error. Okay, so this is the one we're using in our course in statistics. There are different definitions for margin of error. Margin of error is E, and it depends on the size of your sample, which is N. Okay, so if you have a larger number of people in your sample, you're going to have a larger number under the line here. Okay, and if you have a larger number as a denominator, the value of the error as a whole will be smaller. So more people or more data, smaller error. Okay, so let's see how this works. So where N is the sample size. In Linton's case, if you recall, the campaign manager asked 500 people. So the margin of error is 1 over the square root of 500, which when you calculate it comes out at 0.045. Okay, so this is how far out we reckon the result could be. Okay, if you want to just relate that to percentages, multiply by 100 and you get 4.5%. Okay, so the result from the 500 people in the sample could be out, or we expect might be out by 4.5%, so from the true value. So the true value could lie up to 4.5 above our result from the sample or below. So in Linton's case, we saw that the margin of error was 0.045 or 4.5%. This means that given the sample size, the real population proportion P could lie up to 4.5% above or below that sample result P hat. Okay, so let's write that down and see what it looks like. We can write an interval to include the probable value of the true population proportion. Okay, so firstly, an interval gives you a starting and finishing point, or a from and a to, and between these two values it will include the probable value of the true population proportion. So notice that the word probable is used. It's probably, okay, not for certain, but probably. Okay, so what are we saying here? This is our interval. Okay, so we're saying from this value. So this 0.52, that came from the sample. Okay, 52%. We take away our margin of error, which was the 4.5%, and then our true population proportion P should lie between that, when you take away the margin of error, to the value you get when you add the margin of error onto the sample proportion. Okay, so let's see what that works out as. Okay, so when you subtract and add, what we're saying is that the true population proportion P most likely lies between 0.475 or 47.5% and 0.565, 56.5%. So it's quite a wide interval, okay, given that she only asked 500 people. Okay, and this means that the true population value probably lies between 47.5% and 56.5%. Okay, so there is still a chance that Linton might not get a majority here. What should the campaign manager do? She should go ask lots more people. Confidence intervals. On the previous slide, we said probably. We said that the true population proportion probably was between 47.5 and 56.5%. Probably. So how confident can we be in this? How sure? This comes down to definition. By our definition of the margin of error E, okay, so we said E is equal to 1 over root n, we can be 95% confident in saying this. Okay, there are other definitions of margin of error in statistics that can give you a higher percentage of confidence. Okay, but we're not doing that in this course. Alright, so writing what we've done here, the true population proportion, that's regular P, lies between the sample value, P hat, minus your margin of error, which was 1 over root n, and up to the sample value plus your margin of error. So we can be 95% sure in saying that. Okay, and this is known as a 95% confidence interval. So remember, interval gives you a starting point and a finish point. Okay, so whenever you see those words 95% confidence in your exam paper, you need to start thinking margin of error. Okay. Margin of error and confidence intervals. So here's our definition for the margin of error, 1 over root n, and here's a table that shows how the sample size affects the margin of error. So if you have a small sample, like 25, you see you get a very large margin of error, which is 20%, and so your confidence interval is really wide, okay, and it's not much help. All right, as the sample size increases, there you can see 100 gives you plus or minus 10% of an error, okay. And as you increase, you can see if you go right up to 10,000, you've plus or minus 1%. Okay, now in reality, okay, in businesses, etc., or in marketing, basically 100 would be seen as the minimum useful sample size, okay, and then up to about 1,000 would be deemed enough. Okay, if you go more than that, if your sample size is too large, it starts to cost a company too much to run a survey, okay, and it becomes impractical. So in reality, sample sizes between 100 and 1,000 would be the normal. If you can get up to the 1,000, that's great. It gives you plus or minus 3%. Okay, this would be ideal. All right. More than that gives you better statistics, but it might be difficult practically to run your study. Okay. This is the definition of margin of error for a 95% confidence interval. That's your E equals 1 over root n. And there are other definitions we discussed which result in a different level of confidence. So let's try an example. A random sample of 400 persons are given a flu vaccine and 136 of them experience some discomfort. Construct a 95% confidence interval P for the population proportion who might experience discomfort. So the drugs company has done this study and they want to make a conclusion from it about the full population. So let's take the information in the question. A random sample of 400 persons, well, that's N. Okay, given a flu vaccine and 136 of them, we'll have to use that, experience some discomfort. Construct a 95% confidence interval. So we said if you ever see that phrase, you need to start thinking about margin of error. Okay, for the population proportion who might experience discomfort. So let's calculate the margin of error. E equals 1 over root n. Now this is not in your formula books. You have to learn that. Okay, so it's 1 over the square root of 400. So use your calculator to calculate that. What you'll get is 0.05 or 5%. Okay, so that's our error. Now let's recall, to make your interval, your confidence interval, you take the true value P from the population, and we said that it lies somewhere between the sample value P hat, take away your error, and the sample value, add your error. Okay, so this is our interval. So the next question is, what is our sample value? What is P hat? Okay, so reading again, a random sample of 400 persons are given a flu vaccine and 136 of them experience some discomfort. So that's how we're going to use the 136. So 136 of them out of the full 400 of them experience discomfort. So on your calculator, divide 136 by 400 and you get 0.34 or 34%. Okay, and that's our P hat. So let's fill in our values. So we'll have 0.34 minus 0.05 and 0.34 plus 0.05. Okay, and that will give us a confidence interval of 0.29 and 0.39. Okay, now what does that mean? We say that somewhere between, so let's change it back into English, between 29% and 39% of the population, so when they roll out this vaccine, will experience some discomfort. So we're 95% of the sure or confident of those figures. All right. Another example. A drugs company produced a new pain-relieving drug for migraine sufferers and claimed that the drug had 90% success rate. A group of doctors doubted the company's claim, and they prescribed the drug for a group of 150 patients. After 6 months, 120 of these patients said that their migraine symptoms have been relieved by the drug. At the 95% level of confidence, can the company's claim be upheld? So let's see. So, as soon as you see that phrase 95% level of confidence, we're talking margin of error. Okay, and for margin of error, which is equal to 1 over root n, we need to know the sample size. So they prescribe the drug for a group of 150 patients. So that is our sample that they're studying. So 1 over root 150. Okay, and let your calculator calculate that. 1 divided by the square root of 150 gives 0.082. Okay, so it goes 816, whatever. I round off to 0.082, which is 8.2%. Okay, now next we need to create an interval. And the purpose of this interval is to see, does it agree with the claim of 90%? Okay, so remember, your interval is the sample value minus your error and the sample value plus your error, so the true proportion would lie between those two values. So now we need to know the sample proportion. Okay, so this is in reality what happened. After 6 months, 120 of these patients said that their migraine symptoms had been relieved. So it's 120 out of how many? Well, there was 150 in the sample. So let's calculate that. So I get 0.8 or 80% of them. Okay, said they were relieved. Okay, let's do our interval. Okay, so 0.8 minus 0.082 up to 0.8 plus 0.082. Let's do the subtraction and the addition. So the subtraction gives me 0.718 or 71.8%, and the addition gives me 0.882 or 88.2%. Okay, so what does it say? So the population proportion, so translating to English now, lies between 71.8% and 88.2%. So what can we say about the drugs company, their claim? Okay, can the company's claim be upheld? Well, we're 95% confident that no, the company's claim is not upheld. Why? Because 90% is not within our confidence interval, it's outside of it, so they claimed too much. Okay, a coin is tossed 1,000 times and heads occur 550 times. At a 95% confidence level, does the result indicate that the coin is biased? So firstly, what is biased? It means that the coin is not fair. So when you toss a coin, the chances of getting heads or tails should be 50-50, half and half. Okay, so here we see that it's not 50-50 exactly, 550 times. Okay, but that could happen, right? But let's do what we're asked here. 95% confidence level, we'll have to do the margin of error. and the coin was tossed 1,000 times, so that's our n. 1 over root 1,000, and calculate that, and I get 0.032, rounding off there to 3.2% is the margin of error. Okay, remember the true proportion should lie between the sample minus the error and the sample proportion plus the error. Okay, so sample proportion p hat is, so what actually happened? Well, 550 times the coin landed on heads, 550 out of 1,000. Okay, 50 divided by 1,000, and we get 0.55. Okay, so the true proportion is likely to lie between 0.55 minus 0.032 and 0.55 plus 0.032. So let's do the subtraction, and we get 0.518 and 0.582. So what's that saying? It's saying that the true value for the coin in question, if you were to toss it any amount of times, lies between 0.518 and 0.582, so more than 50% in both cases. Okay, so I would say this coin is likely to be biased, okay, based on this sample, because you don't get the 50% does not lie within the interval, okay, is outside the interval. Now, okay, why don't you try some work on that with the quiz and the written exercises. And here's a small glossary.